Okay, this is lesson 2 in the Pythagorean Theorem unit for Math 8. We're looking at the Pythagorean Theorem today, or the Pythagorean relationship. I'm going to start today with a quick demo from YouTube showing this relationship because I think it creates a good visual. You can see a lot of demos like this if you just Google Pythagorean Theorem water demo. It's a common one to come up. So this is, I'm going to play this. What I want you to take note of before we press play is what shapes you see on the screen there. So we see a yellow triangle in the middle, and it has a right angle in the corner. And then we see 3 squares on one on each side of that triangle. So 2 smaller blue squares, and then 1 large clear square at the top. So maybe make a prediction of what you think is going to happen in this video. It does involve some water, and then I'll press play and we'll see what happens. Okay, so we see that the 2 smaller squares, when turned upside down, all of their water completely filled the larger square. And then when you turn it the other way, we'll see that the 2 smaller squares get filled up again. So this is essentially the Pythagorean relationship, or the Pythagorean theorem. When we draw squares on each side of a triangle, it has to be a right triangle. Then the area of the 2 smaller squares equals the area of the larger square. Okay, so let's get into the lesson knowing that. I recommend you use, if you're taking notes today, it'd be good to have some highlighters with you so that you can label your triangles like I'm doing. So see, we have here a right triangle in the middle, just like we saw in the video. I'm going to label the 2 smaller triangles with blue, and then the larger triangle, or sorry, the larger square, the 2 smaller squares in blue, and then the larger square in yellow. Okay, so a couple of terms to start off with here. Whenever we have a triangle that has the square in the corner, that means it has a 90-degree angle there, a perfect corner. And the side that's directly across from that 90-degree angle is always the longest side on your triangle. And it has a special name. It's called the hypotenuse. Okay. And then the 2 smaller sides adjacent to that 90-degree angle, we call those the legs. The hypotenuse is always the largest side, and it's always across from the 90-degree angle. Okay. We are also going to use letters often because the word hypotenuse is kind of long to write out. And so instead of using the word hypotenuse and legs, we're just going to label the side lengths with letters. We usually use A, B, and C to represent the different sides. Okay, so what we saw in that video was that the area of the 2 blue squares equaled the area of the yellow square. So if I were to write down what the area of this blue square equals. So it's a square, so the side lengths are both the same. They'd both be equal to A. So the area would be A times A, or simply A squared. Same with this larger blue square. The area would be B times B, or simply B squared. Okay. And then the area of this very large square on the hypotenuse would be C times C, or simply, I'll just erase too many equal signs there, or simply C squared. Okay, so the Pythagorean relationship is that the 2 blue squares add up to equal the yellow square. So A times A, or A squared, plus B times B, or B squared, equals C times C, or C squared. Area of the blue square plus the area of the other blue square equals the area of the yellow square. So this is only true for right triangles. This relationship does not hold for any other type of triangle. So what we're going to work on today is using this relationship to determine if we have a right triangle or not. Because in the real world, you don't always have a protractor on you, and you can't always measure angles. And so, but if you sometimes it is easier to access a ruler, and so sometimes we do know the side lengths, and we can use those to see if we have a right triangle or not. Okay, let's have a go here with some examples. So here in these two first examples, it's just getting used to the rule. So I'm going to use the same color. So the two smaller squares are the ones that are next to our right angle. And then the largest square in yellow here is going to be the one that is across from the right angle, the hypotenuse. Okay, so we know that the area of the two blue squares adds up to the area of the yellow square. So we know that the yellow square must be 9 centimeters squared plus 16 centimeters squared. So the yellow square equals 9 plus 16, which is 25. And I'm going to use the proper units here. Whenever we're measuring area, we use units squared. So centimeters squared, for example, in this case. Okay, great. Now let's have a look at the next example. If you're feeling pretty good, you can pause the video here and try it yourself, or you can do it along with me. So I'm going to label again the two longer sides, the longest side, which is this one. It's the one that's right across from the right angle. This is my largest square. And then my two smaller squares are these two. So this time, this question's a little bit different because we have the area of the largest square, but we don't have the area of one of the smaller squares. So if we have the largest square, we're going to subtract to figure out the smaller square. So it's going to be, not c squared. Let's actually label. Let's call this one a squared. Let's call this one b squared, and this one c squared. So we're going to write b squared equals c squared minus a squared. 169 minus 25. And we get 144, and the units would be meters squared because it's an area. Okay, so if you have the larger square, you're going to subtract to find one of the smaller squares. Okay, now let's use the theorem or the relationship to figure out if we have a right triangle. So this is probably more likely how you would use it in the real world. So if you were given a triangle and you weren't sure if this looks like a right angle, but maybe it's slightly off, we want to figure out if it's exactly a right angle or not. We can use the relationship. So this is how we do it. We want to label our sides first. That's always the first step. So let's call this side A. We always call the smaller two sides A and B, and then the largest side is C. Okay, and I'm going to use the same colors again, blue for the smaller two sides and yellow for the largest side. So we want to see if a squared plus b squared really does equal c squared. If it does, then we know we have a right triangle. So let's see, let's test it to find out. Now this time we haven't been given the area of the square, we've just been given the side length. So I have to do 7 squared here, plus 9 squared. So I actually have to square those numbers. So it'd be 49 plus 81, and that equals 49 plus 81 is 130. So that's what a squared plus b squared equals. Now let's do, I'm going to give myself a little more room. Now let's do c squared and see if it equals 130. If it does, then I've got a right triangle on my hands. If it doesn't, that means the Pythagorean relationship does not work for this triangle and we don't have a 90-degree angle. So let's see. So c squared would be 11 squared. 11 times 11 is 121. So because these two are not equal, a squared plus b squared does not equal c squared. That means this is not a right triangle. Okay, well, let's try the second one here. You might consider pausing the video here because this question is quite similar. So you could try it on your own, or you can do it with me. Okay, so we have A, B, and C. Let's label our sides. So A, B, and C. And we're going to see if A squared plus B squared really does equal C squared. So a squared would be 9 squared plus 12 squared. So 9 times 9 is 81. 12 times 12 is 144. Just going to color them in. And 81 plus 144 happens to be 225. Okay, so that's a squared plus b squared. Let's see if it's equal to c squared. So c squared, I'm looking at the yellow side, the longest side, and it's going to be 15 squared. So 15 times 15 is 225. So here we see that a squared plus b squared does in fact equal c squared. So that means this is a right triangle. Right. And that's your introduction to the Pythagorean relationship.